this is revision for the second physics topic, forces in motion. The first thing that you need to understand are the names of some different forces. Here is the table. I strongly recommend pausing this video now, figuring out, do you understand what these forces are? And I just want to explain upthrust because it is one that students often misunderstand. So boats are very, very heavy. They have a strong weight force acting down. So why don't they sink? Even if they're made of metal, why do boats not sink? Well, that's because they're full of air, which is less dense than water. So overall the boat is less dense than water, so it floats. And the water is forcing them upwards through a force called upthrust. So anything that floats has a strong force of upthrust on it. But if you dropped a penny in air and it hit water, what would happen to its motion as it went through the water compared to air? So I'll say that again slowly. So if we dropped a penny in air, then it went through some water, would it go faster in the air or in the water? So it will go faster through air, and the reason is because even things that sink also have a force of upthrust on them, and this would slow them down in comparison to air, and that's because a penny has a more similar density to the water. Water's a lot heavier than air, so pennies move slower through water than they would through air. And one more thing about upthrust, so it also happens in gases, and this is the reason why hot air balloons float and why helium balloons float in air also, because the hot air in a hot air balloon is less dense than the cool air around it, so it has more upthrust, and helium is less dense in air, so the helium balloon floats in air. And the last thing I want to add about forces is the engine force is sometimes called thrust, but if you're happy now to move on to resultant forces, we'll move on. Just checking a little misconception. So you're sitting in a chair, your weight goes down into the chair, so your weight is pushing downwards. What is the force? How the chair is pushing up on you? What is the name of that? Answer now. That is not upthrust because the chair is not made of a liquid. That is called the normal contact force. So the normal contact force happens in solids. So if you got that wrong, sort it out. So this is physics, so there's obviously going to be some maths involved, and you have to be able to calculate resultant forces. So a result is something that you're left with at the end. So a sports result is what you're left with at full time. Resultant forces are what you're left with at the end when you add two different forces together that are going in the opposite direction. So I'm going to show you how to do one. So here we have a force up of 5 newtons, a force down of 10 newtons. Which one's bigger and how much bigger is it than the other one? Well, the force down 10 newtons, that one's bigger. How much bigger is it? So 10 take away 5 is 5 newtons. So that is the resultant force. And it's as easy as that. One other way of looking at this is if we take the upward direction being a positive number, so 5 newtons up, and we have therefore minus 10 newtons because that's going in an opposite direction. So this is a more mathematical way of looking at it. If we add them two numbers together, then we'd have negative 5 newtons. So if we're saying the upward direction was positive, then that therefore must be 5 newtons in the downwards direction. So please pause the video now. Make sure you can do these. And the answers in 3, 2, 1. So remember that forces are vector quantities. So you need a direction. They should all have arrows on. And if you got any of these wrong, then I have lots of other questions for you to try now. So can you please pause the video and I will give you the answers in 3, 2, 1. So hopefully you're doing these on a scrap bit of paper or something. And just a little note, so when forces are the same up and down, for example, like the second one, then you could write 0 newtons. But what I prefer is to write that these forces are balanced. So again, pause the video, double check that are any of these other ones balanced. Did you use that word? Okay, so a quick note on the last one there, because that was quite tricky. So in the vertical up-down plane, that you've got 10 newtons up and 10 newtons down, they balance each other out. So you would have no overall force up or down, but left and right in the horizontal plane. And students often get vertical and horizontal wrong. So one way I remember it is by thinking of the curve of the earth. So looking as far as you can see, that's called a horizon. So if you can see a sunrise or something, and that obviously goes from left to right. So horizontal is left to right. And overall on this example, we had 50 newtons to the left and 5 newtons to the right. So our overall resultant force is 10 newtons to the left. So you need to know 3 of Newton's laws, and the first 2 kind of come in a pair, and they're all to do with them force diagrams. So Newton's first law is if the forces are balanced. So if there's no resultant force, if the forces are balanced, what will happen to that object? So Newton said that if there's no overall force acting on an object, it will either stay still, or if it's moving, it's going to stay at the same speed. And if we use a car as an example, so if the engine, the thrust is forcing the car forwards with a force of 100 newtons, but the amount of friction and air resistance adds up to 100 newtons in the opposite direction, so that car would remain at a constant velocity. And if you've been in a car and a car's going at a steady speed, you'll know that the engine's working, but you've probably never really thought, so that what the engine's doing is just balancing the forces, trying to slow the car down. So Newton's first law, very simple. If the forces are balanced, an object will remain at the same velocity. So his second law is about if forces are unbalanced. So if we take that car from the last example, and if that person takes their foot off the pedal, there's going to be no engine force anymore. So the only force acting on that car is 100 newtons to the right. So Newton's second law happens anytime there's a force diagram where one of the forces is bigger than another. So here we have a resultant force to the right. So what's going to happen? So the car will accelerate to the right. So that is a very, very important point. It will not move to the right, it will accelerate in that direction. So the car's moving to the left, but if these forces were acting on it, it would slow down. And how much it slowed down would depend upon 2 things: how big that force is, and also how much the car weighed. So Newton's second law is often written as force equals mass times acceleration. So if there is an overall unbalanced force on an object, it will accelerate, it will speed up in the direction of that force, or slow down in the direction of that force. And things that are more massive, things that are heavier, they need a bigger force to change their directions. That makes sense. You could move your friend who was sitting in a shopping trolley, for example, but it would be very, very difficult for you to move your friend in a car, because the force that you can put in is not going to accelerate them, because cars have a really, really high mass. So a comprehension question for Newton's second law could look something like this. So this vehicle and the people in it have a total mass of 1,000 kilograms. What would the acceleration be for this? Pause the video and make sure you know how to work these out. Well, the first thing we need to do is to rearrange that equation, because we have a mass and we'll have forces, but we're going to be working out the acceleration. And that is it rearranged. So acceleration equals force divided by mass. Substitute in the correct numbers. So the overall force there is 700 newtons to the right, and you need to divide that by the mass. So that vehicle would accelerate at a rate of 0.7 meters per second squared to the right. And it's worth remembering here that acceleration is a change in velocity, and because velocity is a vector, it has a direction, then acceleration is also a vector quantity, and it must also have a direction.